Let's try to understand Dijkstra. It is single source shortest path algorithm. So what you have to do is you have to find the shortest path from source node to all others, all other nodes. Okay, so you have to find the shortest path from the source node to all other nodes. Now, what do you mean by that? Suppose you have a node uh, 1, 2, 3, right? And you have a path like that also which takes up to which takes a weight of suppose 2, it takes 1, uh, it takes 0, suppose, but not negative. No negative rates. No negative rates. Okay, we will come to this later. First, understand what we are trying to do. So there are two paths. Suppose this is source path, and to reach from 1 to 2, the cost is 1, or we can say the distance is 1. To reach from 1 to 2, or 1 to 3, there are two paths. There are two paths. What will be the first part? The first path is this, and the second path is this. Suppose this is path 1, and this is path 2. So for path 1, the distance is 1. For path 2, the distance is 2. Which one is shorter? The path 1 is shorter. So we have to find the like that. This is 1, this is 2, this is 3. So from 1 to 1, 0. Distance from to reach from 1 to 2, the distance is 1. To reach from 1 to 3, the shorter distance is 1. So this is the possible answer. Right? Yes. So we have to find that. Okay. Now to implement Dijkstra's algorithm, so we have the urgency list. This is the graph here, and we have the distance array, and we have the priority. So let's assume the source node is 0, and we have to find the minimum distance to all other nodes. That is, what is the minimum distance to reach 1? What is the minimum distance to reach from 0 to 2? What is the minimum distance to reach from 0 to 3? Okay. So from the source to source, the distance would be uh, 0, right? Minimum distance is 0 from source to source, and for the other nodes, we initialize the distance with infinity. Okay. So let's put it into our priority queue. That is, distance is 0 and node is 0, right? So let's get the 0, 0 out. So we have a 0, 0, 0. So the distance to reach 0 is 0 and the node is 0. Okay. Now what we have to do is we have pop out it, so we erase it from the priority queue. So what's the thing is that now we go to the its adjacent. From 0 we can go to, see here, we can go to 1 and we can go to 6. Okay, we can go to 1 and we can go to 6. Now from 0 to 0 the distance is 0. Now from 0 to 1 that is the cost will be 1, and from 0 to 6 the cost will be 7, right? Now if we go to 0 to 1, the distance is 1, but the current distance is infinity, so we have to update it because we got the minimum distance. Yes, we got the minimum distance, so we update it with 1. Okay, and as we update, we got the minimum distance, we put it into the priority queue with the distance 1 and the node. Okay, now this is done, and we can go from 0 to 6 at a distance of 0 plus 7, which is 7. Then we got the distance of 7 to reach 6. To reach 6, we got the distance of 7. So, but the current distance is infinity, so we will update it. We will update it with 7, right? So we will done with the node 0, and we also put it into the priority queue. So let's put it into the priority queue with a distance of 7 and the node is 6. Okay. Now with the minimum distance, the node is 1, so we pop out it 1, 1. So we have a distance of 1 with a node 1. Now from node 1, where we can go? From node 1, we can go to 2, we can go to 7, we can go to 0. Okay. So from node 1, we can go to 0, we can go to 7, we can go to 2. From 1 to 0, the cost will be 1. From 1 to 7, the cost will be 9. From 1 to 2, the cost will be 0. Okay. But from 0 to 1 till now, from 0 to 1, we have the minimum distance of 1. Right. Now from 0 to 1, we can go from 1 to 0. There is no point to add one more because 0 to 0, we have the minimum distance is 0. So this we will not going to consider. Right. Now from 1 to 7, we can go from 0 to 1 at minimum distance of 1. From 1 to, we go to 7. So we reach ultimately from 0 to 7 at a distance of 1 plus 9, which is 10. Right. But the current distance to reach 7 is infinity. So we will update it with 10. Okay. Right. So we are done with this. From 1, we can reach to 2. So from 0 to 1, the distance to reach from 0 to 1, the distance is 1. And from 1 to, we can reach to 2. So ultimately, we can reach from 0 to 2 at a distance of 1 plus 2, which is 3. Right. As you can see here also, from 0 to 1, we can reach at a distance of 1. From 1 to 2, we can reach at a distance of 3. So ultimately, we can reach from 0 to at a distance of 3. I hope you got this. Right. So, but the current distance of 2 is infinity. So we will going to update it with 3. Right. And we will put it into the our priority laws. So that is it. And we will put it into the priority with a distance of 3. The node is 2. Okay. So we are done with this. Now, which we will going to consider next. Yes, 1. I think we are done with the 1, right? Yes, we are done with the 1. Now, let's get 3 to node 2. Okay. So the node distance is 3 from 0 to 2. To reach from 0 to 2, the minimum distance is 3, and the node is 2. Right. Let it is it. Yes, we will pop out it. We popped out it. So from 2, where we can go? Where we can go? Let me erase it also. Yes. From 2, we can go to 1, we can go to 3, we can go to 1, we can go to 3. And the cost is, from 2 to 1 is 2, from 2 to 3 is 3. We can reach to 2 at a distance, we can reach to 1 at a distance of 1. By 2 to 1, the cost is added. So we will not going to consider it because we have the minimum distance. From 2 to 3, we can reach from 0 to 2 at a distance of 3, and we can go from 2 to 3 at a distance of 3. So we can ultimately go from 0 to 3 at a distance of 6, right? From 0 to 1, 1, from 3, 3 plus 3 is 6, right? So, but the current distance is infinity, so we will going to update it with 6. Let's update it with 6. Okay. Also, let's put it into the priority queue, that is with a distance of 6, node is 3. And we are done with this also. So let's erase it. Okay. Now what the next is? The next is 3 node with a distance of 3. So we have a to reach from 0 to the distance is 6, and the node is 3. Now from 3, where we can go? From 3, where we can go? From 3, we can go to 4, we can go to 2. We can go to 2, we can go to 4. Okay, the cost is 2, the cost is 4. So there is no point to consider again this because we have the minimum distance to reach 2, that is 3. Okay, so from 0 to 3, the distance is 6. From 3 to 4, the distance is going to be 4. So we will add up to it 10. Okay, but the current distance to reach 4 is infinity, which is greater than 10 ultimately. So we will update it with 10, and we will put into the priority queue also. So yes, so the distance is 10 and the node is 4. Okay, perfect. Now what we will consider next? We will going to consider so we will consider this. So next we will going to consider 7 6, that is node 6. To reach is from 0 to 6, the distance is going the minimum distance is 7, right? Now from 6 we can go to the 7, we can go to the 0, we can go to the 5. From 6 we can go to the 0, we can go to the 7, we can go to the 5. Is there any point to add to go from 6 to 0? No, because we have the minimum distance 0. Now 6 7, we can go to the 6 7. The current distance to reach 7 is 10. and from 0 to 6 the distance is 7. We can go from 6 to 7 at a distance of 8, which will add more because 8 plus 7 is 15, which is greater than 10. So let's understand it very carefully. Understand it very carefully. Let me clear it. Yes. So from 0 to reach 7, we have two paths. One is this, and the second one is this, and this one also. Right, this one also. So there are three paths, but we have the minimum one, that is one. This path 1 plus 9 is 10. We will consider we considered it, right? Now from 0 to 6, the current distance is 7. We will add up to more 8 to from 6 to 7, so it is going to be 15, which is greater than 10. We will not going to update it. Okay. Now from this path, we will not till now we will not consider it because we are uh, because that's the minimum one we will get, right? Now let's consider sorry, yes, let's consider now. So we will consider we considered this also. Now from 6 to 5, from 0 to 6 the distance is 7, from 6 to 5 is distance is the distance is the distance is from 6 to 5 the distance is 6. So the ultimate distance is going to be 13, but the current distance is infinity, so we will definitely going to update it with 13. So this is 13, right? So we will be done with this node 6, and we will put it into the priority queue also, right? So we are done with the node 6, but as we update 5 node with a distance of 30, right? So it going like that. Okay. Now next is consider next we will going to consider 10 comma 4. So from 0 to 4 the minimum distance is 10. From 4 we can go to the 5, we can go to the 3, right? So we will not consider it because we have the minimum distance to reach 3, so we will not go to consider it. From 4 to 5 the cost will be 5, and from 4 to 5 the cost will be 5. The ultimate cost from 0 to 5 is going to be 15. But to reach 5 we have already minimum distance, that is 30. So we will not going to update it, so we are done with this also, right? Now the next is 530, and now the next is 530, next is 530. Okay, 30. So from 0 to 5 we can reach at a distance of 30. We can reach at a distance of 30. So distance is 30 and the node is 5, right? From 5 we can go to the 6. From 5 we can go to the uh, 4. So we will not going to consider it because we have already minimum distance for 4, that is 10. So from 5 to 6 the cost is 6. So 13 plus 6 is going to be 19. We have the minimum distance for 6, that is 7, right? So we will not going to consider this part. So as you can see that we will for previously we have seen that there is 3 paths to reach at 7, right? There are 3 paths, right? But we have the minimum one already, that is 6. We have the already minimum distance to reach at 6, that is this 7. This is not the path to reach at 6, right? So by using priority queue we will ensure that we trace the minimum, right? So that's the intuition of complete algorithm, that we have to get the minimum first, and we have to update the distance again and again if we got minimum. If not, then we will not going to consider it, right? So this is the distance. All this is the answer from 0 to 0, from 0 to 1, from 0 to 2, from 0 to 3, from 0 to 4, from 0 to 5, from 0 to 6, from 0 to 7. The distance would be 10, 7, 13, 10, and then again 2 to 7 is 10. Yes. So this is the distance array we have got. Okay. So the question arises, why priority queue only? Why priority queue or set, not queue? So the answer is, if we are using queue, we are not going to trace minimum, right? We are not going to trace minimum. So there might be case we have to do some extra iteration. So that's why we are not going to use queue, right? Now, how set maintain the minimum? As you know that set uh, store the element in increasing order, right? So we can trace the minimum by getting the first element, and we can pop out by functionality erase, right? So as we pop out, we can do it in a set by using erase, or as we extract out minimum, so we can do it by taking first element of the set. Okay, so that's the case. So let's implement it. Uh, let's see the code. So we have given adjacency list and source node, right? So let's call it. Let's declare the size. Let's put the size of the adjacency list in n. Okay. Let's declare the distance vector, the distance of size n, and we have to initialize it with maximum. Okay. Now distance of source equals to 0. Now let's declare the priority queue, and we have to store it. We have to store distance and node in it. So we have a distance and node. Okay. So we are storing it in here, and that's the way to declare priority queue, right? And we have greater, we have to declare greater. We have to declare minimum. So we are using greater, uh, comma, and p, right? So first we have to push initial node, that is with distance 0, comma source, while node peak dot empty, while peak node empty. So first we have to get uh, minimum, the node which has a minimum distance, pq dot top. So node equals to it dot second, and we have the distance, minimum distance equals to it dot first. Okay. Now we have to traverse all the adjacent node for auto adjacent node in adjacency list of node, right? So we have to take adjacent node. Okay. Now we have a node. We have a, let's make it. Yes, we have adjacent node equals to. Let's make it in iterator form, right? And we have the adjacent node equals to I dot second, and we have this. We have weight equals to I dot first. So this is I dot adjacent node I dot first, and we have adjacent weight equals to I dot second, right? If d plus w, the distance plus weight is equals to the distance of adjacent node, so we have to update it. So distance of adjacent node equals to d plus w, and we have to push it into the priority queue also. Adjacent node distance formats. So we have the current distance is distance of adjacent node, and we have to put also adjacent node. Okay. Now after getting the minimum element, we have to also pop out it. So pq dot. Okay. Now just return the distance vector. Let's check it once we have correct all the things, correct or not. Yeah, that's looks perfect. 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 So let's compile it. It looks perfect. Yeah. So it's compiled successfully. Let's try to submit it. Mm. Yeah, it's run successfully. So now let's the time complexity we are using priority to the worst. In the worst case, the time complexity is big of e log v, right? E log v, e log v. Okay. We discuss the time complexity in detail in the next lecture, right? First, let's say how to do it with set. Okay, how to do it with set. So we have to declare set. Let's declare set. We have to store it in pair in comma int. Okay. Now instead of set, we have to declare set as s dot empty. Now we have to get the minimum starting element, so we can do it like that. S dot begin. Okay, s dot begin. Yeah, yes, s dot begin. We have to erase it. So let's erase it as dot erase id, and we have to insert, instead of pushing we have to insert as dot insert, and what's the next thing is, I think it's looks fine. Yeah, let's try to compile it. Hmm. Where? Yeah, instead of push we have to insert as dot insert. To do it like that. Yeah, it looks fine. Let's try to submit it. Yeah. So this is how we can do it with set. Okay. So that's the code for the set. Now one more thing to discuss is why negative weight cycle aren't. We cannot implement the Dijkstra with an. We cannot use the Dijkstra algorithm with the negative weight cycle. Okay. So you can see that we are updating the distance if we get the minimum, right? If we get the minimum. Now, if they are negative weight cycle, we are if we add negatives, so it becomes more negative, which is the lesser. Which by adding negative, we got the lesser, right? But by adding, we have to get the greater, so we can compare it with the current one, right? If we adding negative, we always get the minimum, so it get turns into the infinite loop. Okay, so that's why we are not using the we cannot use the Dijkstra with the negative weight cycle. Okay, so uh, that's the algorithm. In the next lecture, we are discuss the time complexity in detail. Okay, thank you.